now we hop into just the straightforward case of a rectangular basin tub with a constant cross-sectional area. And I guess my first question would be, what would the volume function look like for this sort of a tub in terms of water level height?
Ooh,
Wait, it's height initial time plus change in height. Well, but it's volume. It's length, width, in parentheses, height initial plus change of height.
Okay, so you're thinking like length, width, that's the cross-sectional area of the tub,
Hmm.
and then times it by H initial plus delta H.
Yes.
So would you say that this is the volume at any height H or a volume at a specific height H?
Any height h that is not lower than height initial.
I like that. I almost like the way you have it written out, I would almost say that's the volume of H final,
Mm-hmm.
right? H initial plus delta H. Totally agree with this, but I'm wondering if we can simplify it even further to just pure geometry for any height H. So you can use H. You don't have to use H initial and delta H. What would you write down?
H of T times L times W.
Yeah, I like that, right? It's like we've got this length times width that's constant, it's not changing. And then we just multiply it by the water level, H, right? Um, Going back to the idea of maximum volume, right? Like at what point will this vessel begin overflowing? What would that what would that number be?
That would be
Capital H times L times
Yeah,
W.
exactly, right? So we've got like kind of our maximum constraint here. And then we've got our variation, right? That this is our function that can work for any height h, because the water is only changing in that direction, really. So now that we have that sort of thing, we might start to talk about change of volume, right? And so for change of volume, there's actually two ways to go about it. One of them would be an algebraic change, and the other would be just a geometric calculation. So which would you like to start with? If you're thinking of one or the other, just shout it out. We'll do both of them.
I guess let's start algebraically.
Yeah. All right. So how would we calculate the algebraic change in volume?
so
Change of.
yeah.
Oh, go ahead.
So the algebraic change in volume would be delta uh delta V of H, or sorry, yeah, delta V. Um, so this is actually a function now, right? So this is
Yeah.
actually okay. So delta V would be equal to length times width times delta little h.
Yeah. I like that. That was a quick way to get there. I would almost argue, Kane, that you did it the geometric way. So I'm going to write that over here because I think what you did was you kind of looked over here and said, well, this light blue slice represents my change, right? And you said, well, hey, I know how to calculate the volume of a rectangular prism. It's just the length times the width times the height of said prism, right? And for the change in volume, the height is just change in height. So I think that's like cutting right to the core, right? But as far as the algebraic method, we're really applying this change operation to the function, right? And when we do so, there's kind of a few extra steps, right? You could say, okay, the change function always takes everything and takes the final amount of everything minus the initial amount of everything. Now, in this case, big L and big W are constants. So those aren't going to change. So it's just length times width times height final minus length times width times height initial. And at that point, it really leads to the same result you got from the geometry because you can factor out the constants. And then you're just left with H final minus H initial, which is the definition of delta H. So the first lesson here, which you skipped right to the point because you've got a lot of experience with it, is that the change operation um, you can factor constants out, right? Or another way to say it, I guess, is just you can pull out constant values, unchanging values. It makes sense, right, that the change operator would not do anything to things that aren't changing. But we get the same result either way.
I'm trying to remember what that's called when it's something over sums, because it's like derivatives are like that, and
Yeah.
like I think like integrals are like that.
Yeah, oftentimes they'll call it linearity. That might be
Yeah,
one of the
linearity.
terms. So at this point, we have, either way we cut it, whether we're looking at the geometry or looking at the algebra, we have delta V is just cross-sectional area times delta H, right? So now at this point, we know exactly how change in volume and change in height are related. So, for example, if I know that my delta V is, I don't know, 1 meter cubed, and I know my cross sectional area is, I don't know, a half a meter cubed, or I'm sorry, a half a meter squared, then what would my change in height be?
2 meters.
Yeah. So it's going to rise 2 meters. And that's a really nice relationship we've got there. We can extend it a little bit more. And, like we mentioned earlier, in terms of water clocks, we're really interested in delta H over delta V because the human eye and brain is so much better at dealing with length than with volume. So we may like divide over the cross sectional area to find the relationship. If you know a certain change in volume, then you just divide by the constant cross sectional area and you get a change in height. Now, at this point, we still haven't really talked about how time enters into the equation, right? So, like, we know it doesn't really matter what time interval it is. If your volume changes this much, your height changes this much, right? So, this equation has nothing to do with time. It's really just set by the geometry of the tub, right? Let's say that we wanted to get time involved. Before the volumetric flow rate, which we kind of have been assuming is constant, what's the volumetric flow rate equal to? And not necessarily a number. I guess I'm asking symbolically.
Delta V over delta T.
Yeah. So if that's something we already know, right? We know delta V over delta T from our faucet at that constant angle and constant pressure source. How could we get delta V delta T into this equation right here?
Divide it by delta T, move the A over to the left side.
Sure. So you're saying let's just divide everything by delta T?
Yes.
Nice. And then on this side, you get delta H over delta T, right? So now we have something, right, that we would refer to as a related rate. So before what we had was a relation of change, really, of change. Like this isn't a rate. That's just how much volume changes. This isn't a rate. That's just how much height changes. And we have them coupled together now. And then over here, now we have a related rate because this is a volumetric flow rate. And then over here, what does delta H over delta T represent?
It is
Height
a
flow rate?
What's that?
Yeah, height flow rate?
Sure, you could call it that, right? It just tells you how the height changes in time, right? How that water level changes in time. I might call it water level speed or velocity. So it's how fast the water level is increasing or decreasing. Now, a question for you here, up until now, we've been talking about constant volumetric flow rates, right? Nice linear accumulation of water. Does this related rate require delta V over delta T to be constant?
Wouldn't that depend on the rate of height in regards to T as well?
Yeah, yeah, absolutely. Because they have to be related in this way, right? We know that delta H over delta T has to be related to delta V over delta T by this one over area term. So we know that much. But I guess what I'm asking is, uh, do we have to have the volumetric flow rate be constant for this relationship to work?
Not necessarily.
So, in other words, I could go turn the nozzle on the bathtub and this relationship would still stay true.
Yes, because they're both in
Yeah.
terms of time, and
Yeah.
volume
So,
depends on height.
yeah, nothing prevents like delta V over delta T from changing. And that's a really interesting and super, this is kind of why the rectangular tub is so nice for calculation, is because we have two factors that influence how our height changes in time. The first factor is set by what? What sets the 1 over A term?
The geometry of the tub itself.
Exactly. Tub geometry. And that's it. And then what sets delta V over delta T?
However, we set our faucet.
Yeah, it's the faucet. And it's safe to say in the case of the rectangular tub that the rate of flow from the faucet has absolutely nothing to do with the tub geometry. We've already kind of seen that in our earlier model where we didn't consider overflow. And at the same time, like the geometry of the tub doesn't change based on the faucet flow rate. So we have two different factors that affect the change in height with respect to time, and they're actually decoupled. So we have these decoupled factors of geometry and time. So kind of, like if I were to draw like a flow chart of this, I would say like time is really we treat it as the basis of everything, right? So everything starts with time. And as time goes on, the faucet pumps out a certain amount of volume, right? And as the volume accumulates in the tub, so does height. notice that there's not a direct through line from time to height, right? And so we just have this nice decoupled system where the amount of time that passes sets how much velocity is in the tub and how much, I'm sorry, sets how much volume's in the tub, and how much volume is in the tub sets what the water level is. And it's nice and decoupled in that sense. Now, could you imagine an example in life, not necessarily of a tub, just think of anything where the geometry and the time component aren't nicely decoupled like this?
Calc 1 gets this really annoying problem about someone walking at night with a street light
Hmm.
and you're measuring the length of the shadow.
And so in that case, you would say, hey, the shadow has two factors, right? One of them would be the geometry of the person
I was
and
gonna
the angle at which they stand, or what?
Yeah,
I was gonna say if the faucet was uh underneath the water, uh it
Oh,
might affect the flow rate, the water itself.
that's a really good point. Like, as if the spout were underneath the tub, then as the tub filled higher and higher, there would be more hydrostatic pressure at the entry nozzle. And so pressure would increase outside the nozzle and effectively lower the flow rate into the tub. I think that's a good point, right? Like
oh,
if you were filling it from the bottom, that makes sense. Now we don't have a nice system that's decoupled like this. At that point, the height would start affecting the volumetric flow rate. Yeah.
also like an oddly shaped vase, right? Where
Right?
if
Oh
it
yeah.
like comes in towards the middle, it's going to change height way different
Ah,
than near the bottom.
yes. That's a really good point, right? So like if you had two different vessels and one was tall and skinny, and then you had one that was shorter and wider, the same volume isn't going to result in the same height change, right? We already know that through this relationship. For the really skinny vessel, um, it only takes a little bit of volume because you have a really small area and you end up with a big change in height. So what you're saying, Topher, is then if we combine these vessels, right, and we have some sort of an irregular cross section, I don't know, maybe a vessel like this. Now, at this point, you could almost say that the geometry of the vessel is set by time because at this point in time, where the water level's here, the geometry is far different than at this point in time, where the geometry of the tub is like this. So, even having an irregular shaped tub leads to this coupling, this beautiful separation of geometry and time. It will eliminate that. So that's what we're going to focus on quite a bit for the rest of our time. But I think first I would like to talk about a few more relationships. As far as graphs go, because I feel like the graphs, I'm just going to clear this. So we had delta H over delta T was equal to 1 over cross sectional area, which was constant for this tub, times the volumetric flow rate. Now we're going to draw three graphs. One of them is going to be a volume to time graph. One of them is going to be a volume to height graph. And the last one is going to be a height to time graph. So to start out, and we've already worked through this one once, what would the graph of the volume to time look like, assuming a constant flow rate?
It should
Be
just be a slope, like a normal slope.
Yeah. Slope, maybe some initial volume, but we're gonna say it starts with zero volume in it for ease. What would the slope of this be?
1 over A, right?
Delta V over delta T.
Ah, right.
Yeah, right, right. And this would be the slope. So slope would be change in volume over change in time. Okay, now we pop down to the volume to height function. And let me go ahead and let me write out that formula again that you guys gave me. It's volume as a function of height is equal to cross-sectional area times height. Okay, so what would the slope of this, right, the volume to height graph be?
It'd just be A.
Exactly right. In this case, the slope is A. So slope would be just the cross-sectional area. Like we talked about, if you have a larger cross-sectional area, it takes you more volume for less height. If you have a really skinny cross-sectional area, that's a small slope, you can gain a lot of height with just a little bit of volume, right? Now we go to our last graph, the one we really care about, which is height as a function of time. Now, assuming the volumetric flow rate's constant and we have a constant cross-sectional area, right, which is what these graphs represent, we can say that the height to time graph must also be linear. It's going to be a straight line. What would the slope of this one be?
Just change of height over change of time, right?
Right, it's delta H over delta T. What's that equal to?
1 over A change of volume over change of time.
Right, change in volume over change in time. And then the slope A, right? We've got A over here. Notice what kind of a relationship pops out of that. Can you think of a way to relate the slopes of these three separate graphs? Some sort of algebraic expression.
Well, you should invert the slope of the V and H graph. It's just multiply it to the slope of the V and T graph.
Ooh, good catch. I didn't want to do V to H. I wanted to do H as a function of V, right?
Oh,
So the slope
okay.
there would be good catch, right? The slope there would be 1 over A because height is what we care about, and height is a function of volume. Volume is a function of time. And good point. So what we've really found is that if you want to find delta H over delta T, you can do it by taking delta H over delta V and timesing it by delta V over delta T. Because delta H over delta V is what?
It's 1 over A.
1 over A. So hidden inside this system is an example of the chain rule. Now we've shown it for the linear example. Like I just discussed earlier, nothing in this relationship tells us that delta V over delta T must be constant. Right? We could have like a really funky fill and drain model, and then we'd have to do significant work to figure out actually this function wouldn't change, would it? What do you think? If I went ahead and changed my volumetric flow rate, so I'm having a fun time and I am going to the faucet and I'm changing the angle a bunch, right? So now I have this funky curve, right? What about my H as a function of V? Would that become a funky curve?
No, I wouldn't think so unless the length and the width were changing.
Right.
Because it's going to have to
Yeah.
still stay straight to make keep the length with height rule legit.
Right. Exactly. The straightness of the H as a function of volume is set by the constant cross-sectional area. So that's still going to remain a straight line, even if delta V over delta T changes wildly. And then you would think that whatever funky curve you had for, the different slopes for V as a function of T, whatever kind of funky curve you had for that, probably going to end up with a very similar scaled version of that funky curve, right?
Would it just scale in regards to the H and V?
Yes, it would scale with regards to the cross-sectional area. And that's kind of real quickly before we move on to a non-constant cross-section model, we could take delta H equals 1 over A times delta V, and we could turn this into a true volume function, not a change function, right? This is a change function. If volume changes by this much, height changes by this much. Um, how would we use techniques from earlier to find H as a function of T?
Could you repeat that question?
Yeah, how could we use this change relationship to find an actual H height water level as a function of time?
Well, wouldn't delta V divided by delta H be equal to? Oh no, that'd cancel out. Uh,
Let me give you a hint. What if I wrote H final minus H initial over here, and then over here I wrote V final minus V initial? What would you do next?
Isolate H final.
Right, because H final, we want to turn that into our variable height, right? So we would almost say, like, let's let H final just be height as a function of time. Let's let V final be volume as a function of time. And now we just want to solve for H of T, right? So I'll move over here. I'll say, okay, H of T is equal to 1 over A times volume as a function of time minus 1 over A times volume initial plus what?
H initial.
Plus H initial. Okay. Do you think we can simplify this formula more? Because at this point, what we have is to find height at any point in time. All you need to know is the cross sectional area of the tub and the volume as a function of time, as well as the initial volume and the initial height. Could we simplify this function further?
you can just do 1 over A times V of T minus V I in parentheses and then plus H1.
True, but is there any way, does VI and HI relate?
Yes, they're both
Yeah,
0.
Oh, okay, they could both be zero. We could set them both to zero. What if I just want to do it a little more generally? Do we have a function with which we can relate volume and height?
we're inputting the same T value in for both of them.
Yeah, but don't we have a function that relates them, right?
Oh, yeah. Yeah, we
So we
do.
could just say V initial equals what?
Equals area times height initial.
Yeah. And then we could plug that in for V initial, right? And so now we have minus 1 over A times height initial plus height initial, right? And what happens?
The height initials cancel out, and the
Right.
areas do too.
Yeah, so what you end up with here is you just end up with minus H initial plus H initial. Bam, bam. And you end up with, hey, height as a function of time is equal to 1 over cross sectional area times volume as a function of time. So long as you have volume as a function of time, for this tub, height as a function of time will look exactly the same up to a scale factor, 1 over A. So, I'm not saying that v to t and h to t are exactly the same function, but they have exactly the same scale shape, right? So, say I'm drawing these curves. Is area getting smaller or bigger as I draw these curves?
Getting smaller.
Yeah, so like I'm getting less. Oh, wait, wouldn't I get
Wait,
more height than time if it was smaller area?
yes.
So
Wait,
actually,
smaller. It would be a bigger area, right? Because a bigger area makes a bigger volume, and then the height, we only need a tiny bit more to reach the volume.
exactly. So like if this function represents a equals 1, then this function might represent a equals 2. Because I have a larger cross-sectional area, it takes more time for me to accumulate more height, right? The wider the basin is, the more volume you have to pump in to get more height, just like you were saying. And if I drew one on this side, then that might be a curve where the cross sectional area was 1/2. But the key point to make here is that the height function and the volume function are scaled cousins of each other, right? 1 over a is just a constant for this particular case. All right, so at that point, now we get to think more. By the way, I love this example Nick gave of a case where there wasn't a nice decoupling of geometry and volume, or geometry and time. And that case was a water balloon. So when you're filling a water balloon, as you change volume, you're actually changing the geometry of its container, right? So that would be a
Right.
pretty brutal example of a strongly coupled system. Right here, what we have is about the most decoupled system you could imagine. The geometry sets nothing about time, and the time sets nothing about geometry. The case I thought of was you're sitting in the tub, right? Like, oh man, this used to be straightforward, um, but now like this old relationship that we had, delta H over delta T equals 1 over A times delta V over delta T. What's different now between this case of you sitting in the tub versus you not sitting in the rectangular tub?
You have to keep in mind displacement from the body.
Right, right. The body is clearly changing the cross-sectional area. The body is now almost becoming a part of the vessel in a sense. So what you're dealing with now is you have delta H over delta T, but now it's 1 over area, which is a function of height. So we've got another function you would need to know. Like you would need to figure out, okay, exactly how I'm sitting in the tub. How much volume does my body take up at some cut in height? If I cut it off there, I have to figure out what's the volume of my lower half. So this is not particularly easy to deal with. It's very decoupled because, before we had time increases volume through the faucet, and volume changes the height of the water level. But now the very height itself affects area, cross sectional area, and cross sectional area affects volume accumulation as well. So we've got a strongly coupled system here. I'm not suggesting we try to solve this one. This one would be kind of brutal. Although if I gave you an area as a function of height, you could probably do it. Um, but I'd like to focus on a more geometrically pleasing version, which is this triangular basin. Okay, so the triangular basin was the simplest example I could think of as cross-sectional area being a function of height. And so with that in mind, let's start out with just what would the volume function look like for this tub?
Length times width, and then in parentheses, h initial plus change of h, out of parentheses, plus length times, wait,
Remember, we just want h. We don't need to worry about the
right.
initial delta yet.
I guess, are you now just asking for the formula for the volume of a triangular prism?
Yeah, pretty much, right?
Wouldn't it be 1/2 length width height?
Yeah, where height is the only variable, right? Or wait, is height the only variable?
Width is also a variable.
Yeah, width is a variable now too. So I'm going to write it with lowercase. Okay, so this is true for any height and width. The triangular prism is always half of its bounding rectangular prism, right? So one way you could think of that is you've got 1/2 of your width times your height. 1/2 of width times height gives you this area, and then you simply extrude it by length L. So this would be general. Then, of course, for V max, the maximum volume your vessel could hold, what would that be equal to?
1/2 length times width final times height final.
Yeah, where width final and height final, I'm using these capitals, capital letters. So, oh my goodness, we have two variables. I don't know why I wrote that. This is not volume in terms of height. This is volume in terms of width and height. Is this system multivariate?
Yes.
Okay. Is there a way to make it single variate?
Yes.
Forget, yeah, if we get
How do
width
we
in
do it?
terms of height, vice versa.
Okay. So maybe we could find width as a function of height. What would that be?
It'd be the volume divided by the height times 2.
Well, but we don't want V in here. Or I guess we could plug it in, but then we'll get width again.
It'd be one
So,
half, or wait, sorry.
so we want width just in terms of height.
Yeah, width would be width initial plus change of width. And then in terms of height, wouldn't it be change of height times change of width if we're allowed to do that?
Yeah, I think a change in height, a change in width is a good start there. What
But
if
it that
I drew these 2 points and
I
I
was gonna,
said this is 0, 0, and this is um let's see, W or H and W.
say, isn't delta H delta T equal to some constant times delta W delta T?
Delta H equals what?
Said, isn't delta H over delta T equal to C times delta W over delta T?
Yeah, that seems totally reasonable, right? Because the height and the width are related by a constant because they are related by a straight line, right? That seems totally reasonable. I do think that there's probably an easier way to relate them without time involved at all. But I agree with that statement. How
it's
would
just
you
as
find the slope between here and here?
width it just equals 1 over c height then, right? Or c
Um,
height.
yeah, yeah, exactly. There's just some constant and then times height. We just need to figure out what that constant is. Um, And but we know it's linear, right? Because it's a straight line connecting those two.
That constant would then just be the capital W over capital H, right?
Exactly. Yep. And you know that's the case because if you now plug in what's my width when I plug in my max height, when you plug in your max height to that formula, you get back out your max width, right? So that works perfectly. Another way to think of it would be to say, really, remember, it's equivalent triangles that form a line. It doesn't matter over what distance you measure. So you could say, like, oh, I just need to find some delta W over some delta H and times it by H to find my width. And you just happen to pick the easiest delta W, which is, well, my W went from 0 to W. And the easier delta H is, well, my height went from 0 to capital H. Yeah. So that gives us our width as a function of height. We plug that into our volume formula and we get 1/2 length. Width is now capital W over capital H times H and times H. So we get 1/2 length times width over capital H times H squared. So we've got an H squared term this time. So volume is accumulating kind of in a quadratic relation with height. So now that we have the volume formula, which is nice that we could get it in this case, because luckily we know that triangles are half the area of a rectangle. Now I'd like to focusing on the geometric change versus the algebraic again. So which one should we start with?
Maybe geometric.
Yeah. So you've noticed that as we go from some height initial to some height final, that you can decompose the change in height into a rectangular prism and a triangular prism, right? Like a little triangular wedge. So how would we calculate the total delta V, the total change in volume? It's going to be equal to the sum of the rectangular component plus the triangular wedge. So now we just need to figure out what's the volume of the rectangular chunk, what's the volume of the triangular wedge.
Or the volume of the rectangular chunk would be the change of height times length times width initial.
Mm-hmm.
Then the volume of the rectangular chunk would be change of height times length times change of width.
Yeah, length times change of width times change of height. Almost. You're missing one thing.
1/2.
Exactly, because what you said would be the square
The
version of that,
rectangle,
or the
right?
rectangular version of that. So, okay, we've got this. We could write with initial in terms of height, right? So what's width initial in terms of height initial?
Volume initial divided by length divided by height initial, right?
Well, let's use this one so we don't end up with volume again.
Yeah, yeah. So yeah,
So with, go ahead.
max width divided by max height times height initial.
Yep, that's our width initial. And then how do we find delta W in terms of delta H?
Wouldn't it just be the constant times delta H? So yeah, max width over max height times
Yeah,
delta H.
just like we learned before with the change operator, we can pull out constants. So we could say that delta H or that delta W is equal to width over height times delta H. So we've done those substitutions. Now we distribute and we find something that's kind of cool, which is that we've got this seemingly constant thing, L times W over H, that's in both terms. And then there's something else interesting here. The rectangular term depends on the change in height and also your initial height. The triangular wedge doesn't depend on initial height at all. It only depends on delta H. Why is that?
Because the when we defined del like our initials, it was before there was even a delta H, right?
Okay, let's expand on that a little bit. So you've got some height initials, say here. The rectangular term depends on it. That delta V0, our constant cross section at for the initial point depends on H initial, right?
Right.
So imagine that we cut a piece down here of the exact same delta H. So I cut a piece down here of the exact same delta H. Has the triangular wedge changed compared to
No.
up here? It hasn't. As long as you have the same delta H, you have the same triangular wedge, right?
Hmm.
But what about the rectangle?
The rectangle has changed, yes.
It's changed drastically, right? So that's why the rectangular, or I guess you could call it the constant cross section, it does depend on H initial. Whereas the triangular wedge, look, all those triangular wedges look exactly the same, right? They only depend on the delta H that you're dealing with. But it's also cool because we have a delta H squared here, and we'll get to that in a minute. But I think it's important to see that the change in volume can be decomposed into this rectangle and this triangular wedge. Now let's try it the algebraic way, and we're going to find something really interesting. So you've got delta V equals the change in our V function, which I'm going to write in terms of H because we already did that. Okay, so I'm using this volume function we derived earlier. What's the change in that function going to look like?
It's just the same thing. It's just the H is delta H now.
What do you mean?
So it'd be 1/2 capital L times capital W over capital H times delta H squared.
Delta H squared. Is delta H squared the same as delta H squared?
Um,
Yes.
What do we think?
mm, no,
Why not?
because you're taking H final minus H initial on the left, and then you're squaring that to get the binomials. And then on the right, you're taking uh, you're taking H final minus H initial, squaring it, and then you are
So here you take the change and then you square it, right? Here you take the square and then the change. Are these two things equal?
No.
No, they're not. So we can't treat those as equal. What we can do next, though, is we can say delta V equals, yes, all these constant things that don't change, and then times H final squared minus H initial squared. Do we know of any neat tricks to factor this guy out? What are
This
we
is a
thinking?
Difference of squares.
yeah.
Yeah, so we can get an HF plus HI term and an HF minus HI term. And of course, the HF minus HI term, that's the delta H we want, right? Why don't these two things look the same? We did the algebraic change, we did the geometric change. Do you think they're the same?
I mean, they need to be the same at the end,
Thank
right?
you. Right. They need to be the same. So we're missing something. What does this equation have in it of change that this equation of change doesn't have?
There needs to be like hmm, there's not enough like length, width over height in a weird way. I don't know how to explain
Right.
it.
Over here, there's two that clearly get factored out. Are there any variables in here that aren't in here?
We're missing height. Wait, there's a height final on our right one, and there's
Hmm.
not one on the left.
Right. So if we were to write height final as something else, what could we write it as?
Capital H.
Mm, this is any height final, not necessarily the top, right? It could be
Oh,
any interval.
delta H plus H initial then, right?
Exactly. You could write H final as H initial plus delta H. Then when you distribute everything, erase this line here. Once you distribute everything, you actually do end up getting the same thing. Because notice the HI's combine to get 2HI.
Cancels with the 2.
Exactly. And you just end up with length times width over height times HI. Then you distribute the delta H. Then notice the delta H has an over 2.
Hmm.
There's the 1/2 term. You still get this particular constant. And now your delta H gets squared. Okay, so they're the same thing. Well, why do the algebraic way at all if they give the same thing?
It's just a different way of thinking.
Different way of thinking. I also think it actually brings up a really interesting perspective. Notice over here, what do you think would happen as delta H gets very small?
Change in volume gets really small too.
Change in volume gets really small too, but I want you to focus on this right here. As delta H gets very small, what happens to this?
Isn't that like approach one?
Close, because as delta H gets very small, you could almost say H final is equal to H initial.
Right.
And at that point, then you could plug that in and say delta V equals H initial plus H initial over 2 times length times width over height times delta H. And what does this simplify to give us?
Just H initial times length width over height times delta H.
Right. So we could say delta V is approximately length times width over height times H initial times delta H, right?
Hmm.
Does that look familiar to anything from the geometric change?
It looks like the rectangular prism.
Exactly. Looks like delta V zero. So what we're saying here is as delta H gets very small, the triangular wedge becomes less and less of a contributor to total volume, right? Now, that in and of itself is pretty cool. We're seeing algebra give rise to a little bit of early calculus, right? But I think to really drive it home honestly, we have to look at the geometric picture and say, okay, let's say that the only thing you're varying is delta H. So delta H is the variable. We pick some height initial and we're just varying delta H. This is the rectangular contribution. This is the triangular contribution. And then at that point, let me go ahead and share. Let's see here. Desmos, because everybody loves Desmos. Let's see. Not that one. Let's see. Here we go. Okay. So here I have a graph of, consider this to be delta H, linear. And then here I have a delta H quadratic, right? Now notice that when you're at values of delta H greater than 1, which term dominates?
The linear one. Well,
Greater?
oh, the squared.
Right. So in other words, for bigger delta H, that triangular wedge becomes dominant, the volume of it. But as delta H becomes smaller than 1, which one's dominant?
The the slope, the line.
The linear one, right? And not only that, I just take this picture. At this point, our interval is from 0 to 1, right? Like for values just a little bit less than 1, you really can't neglect the delta H squared term, right? Okay. But now I'm going to zoom into the interval from 0 to 0.1. Okay. Can you even really distinguish this as not being 0? The
Not
further you zoom
really.
in, not really, right? The further you zoom in, oh my goodness, like at this point, that bottom one looks like a line with 0 slope. But the linear one is still just a damn line. It looks exactly the same. But the quadratic one, I can't even tell it's not the x-axis. So this is even just not even from the perspective of limits. This is just practical calculus, right? Like that delta H squared term gets very small very quick. And the linear one, it looks identical no matter how far you zoom in. That's one of the cool things about linear functions is you zoom, 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 and it looks pretty much the same. So the reason why I'm saying that is because I'm trying to give evidence. I'm trying to give evidence that as delta H becomes very small, let's see, I gotta go back a couple. As delta H becomes very small, the triangle term does not matter. As Ahab would say, negligible. Okay. So it's safe to say that for very small delta H, that delta V is just the rectangular part, right? Okay. Now, as we squeeze things very small, we're going to use a special notation, right? Instead of saying capital delta V for change in volume, we're going to change it to little delta V. And we're going to change capital delta H to little delta H. And what the heck? If the interval's small enough, who cares about height final and height initial? It's pretty much the same dang point. So we may as well just call that H, right? We had a finite difference. As we squeeze that finite difference closer and closer, the initial and final almost inhabit the same point. So we may as well just call it H. And then delta H becomes DH. And out of that, I start to answer Nick's question of are differentials fractions or ratios? I would say absolutely yes, right? I can divide over this dH in the same way I could divide over this delta H. There's nothing preventing me from doing that, especially when you look at it from the perspective of just it's a pretty good approximation, right? That's all I'm really trying to do here is say, hey, this triangular wedge, it depends on delta H squared. It shrinks drastically as delta H becomes small. So the second we write dV, we're only going to extract the linear term. Okay? And this is why when we're dealing with calculus, we only care about linear things. You remember earlier we for the linear accumulation, the rectangular tank, we were able to say delta H over delta T equals delta H over delta V times delta V over delta T, right? And at the time I said, well, we've only shown this for constant accumulation, right? We've only shown it for a constant cross section. Paired with the idea that by the time you get to differentials, you only care about linear terms, then it follows that delta H over delta T also equals delta H over delta V times delta V over delta T, because we only care about linear terms. Do we think, I'm just curious, do we think that this would work for finite differences? Does the chain rule work for non-zero interval differences?
Yes.
Let's try it out. Um, we can do it. I think we've got all the formulas we need. So let's figure it out. Let's say, we're looking for delta H over delta T, and we're seeing if it equals delta H over delta V. My Wacom is starting to crap out on me. Delta V over delta T. All right, so delta H over delta V. Um, we've got that. We could probably get that over here, right? We've got the geometric relationship between change in volume and change of height for finite differences. This is where there's 2 points, it's a wider interval. So to do that, we could say delta H over delta V equals 1 over HF plus H initial over 2 length times width over height. Then delta V over delta T, that might be set by the tub or the faucet, right? Delta V over delta T is set by the faucet. So that we can vary it. That's fine. Um, and we're trying to see if it equals delta H over delta T. So let's see here. We've got 1 over all this stuff. Could I flip this? What do you think?
Yes.
So could I write this as 2 capital H over length times width H final plus H initial,
Yes.
and then times delta V over delta T. Okay, so now we need to figure out how do we even get delta H over delta T?
Change the H, or wait, no, you can't do that. Never mind. Um, you'd make the H final a delta H.
Yeah, you could do that, right? We could do that substitution, but what about delta H over delta T? What can we do with this finite difference one to get that? Like using this thing here.
Are we just Going to substitute delta V for that whole equation and then simplify accordingly.
I think we should be able to, right?
Hmm.
Does it work?
Then get delta H on both sides. That's the problem because they are defined in relation to each other.
Okay, let's plug it in and see if we get equivalent on both sides. I think we actually might in this case. Because yeah, you're right. Plug in delta V and just put it over a delta T, right?
Hmm.
Ooh, man, marker is not happy. Let's see. I don't know why, but after like 2 hours, my Wacom just poops out on me.
It just freaks out.
Yeah. All right. Like, let's check it out. This cancels with that. This cancels with that. Those cancel with that. Those cancel with that. Delta H over delta T equals delta H over delta T. So it actually does work for a finite difference in this case, doesn't it? So that's pretty cool. So it worked as a ratio over here. It works as an infinitesimal over here. And that's kind of the point I was trying to bring up to answer Nick's question is differentials are ratios because you can manipulate the finite differences before you compress it into differentials. So this point, actually with the last group, I think we talked about more than one finite difference. So taking the difference of the differences or the change of change. Um, so let's see here. Yeah, rate of change of the rate of change. I think that's a fun thing to dive into. And then next week, we're going to actually go into um, quadratic basin and double linear basin. And we're going to learn a little bit more about those using geometry and algebra. But now I want to talk a little bit about rates of change of rates of change, which would be, for example, well, firstly, if I'm asking about the rate of change of a rate of change from a finite perspective, that's like applying the delta operator twice. Sometimes you'll see it written as like delta 2 V. And this is a little bit trickier because with delta V, you just needed 2 points, right? Or two different volumes, V final, V initial. The tricky part about the change of a change in something is that you actually need two changes to compare change. So, like change from here to here, change from here to here, compare those two changes. So, how many points am I going to need for my change of change?
Four, right?
4 points. Well, how many points do I need for my change?
You need two.
Right. So I see where you're getting at. You're like, I need a change and another change. So 2 times 2 is 4.
Oh, we could just do three though, because then we can do it in terms of that last dot.
Right. So when we're interested in change of change, we really want those changes to be next door neighbors for it to really tell us something, right? So what we're going to do there is keep the delta H the same. We want to leave it the same, right? Like we don't want to compare apples and oranges. Of course, the change in volume is going to be less if my change in height is less. So we keep the delta H's equidistant. And then let me draw with a straight edge here. Bang. So my first change is represented by what? And actually, maybe since we're starting to deal with multiple points, I'm going to label this point H1. I'm going to label this point H2. I'm going to label this point H3. So if I want to know the change in changes, wouldn't that be change in 2, 3 minus change in 1, 2?
Yes.
So it's like, okay, I need to find how much my volume changed as I went from height 2 to height 3. That's kind of represented by this, right? This would be like our delta V from 2 to 3. And then this is the delta V we were dealing with before. That's the delta V from 1 to 2. Okay. So from there, where do you guys think we would go to figure out what the change of the change is? Are you seeing a picture in your head or are you thinking about the algebra?
I'm thinking geometrically because we're just, if we're looking at this as a rectangular prism with a triangular prism that we just attach to the side, then we're just going to do that twice and just subtract the last one from that first one.
I like it. So what you're saying, if I'm hearing you correctly, is figure out what the change in the first one was, which is represented by this, right?
Hmm.
And then are you saying to kind of superimpose that on the second change?
I'm saying get the full length of that second change. It's just subtract it from that first one. So I guess so,
Yeah.
yeah.
Yeah, right. You're exactly right. So I'm going to take this first change and I'm going to move it up to superimpose it on the second change. That's going to help us see what the change in change is. So what area or what volume are we looking at when we say change of change?
We're looking at the volume of the triangular prism, the red one. That one's changing. Since the rectangular prism shouldn't be changing at all.
Right, like that rectangular part didn't change, right?
Hmm.
Neither did the triangular part because I superimposed the second or the first change on the second, right?
Hmm.
So what's left over?
It's that like weird forgot the name of it. Parallelogram that's left
Yeah,
over.
right. It's this parallelogram looking thing. This is the change of our change. This represents delta 2 V evaluated for points 1, 2, and 3. And does it look like we can decompose it into structures we already know?
Yeah.
So you remember
Yes.
before we, oh, go ahead, Kane.
I was just gonna say yes, it does.
What does it decompose into?
Geometry of delta W. Uh, trying to remember the formula.
Uh,
It's
yeah.
sorry.
Oh, no, no, no. Go ahead. You don't. I don't even need the equation. If you could just tell me what shapes it breaks into.
Two triangles.
Two of the triangular wedges, right?
Yeah.
Oh man, Wakeham's not happy. The wedges. And had I not erased the other page, we would know that the wedges are given by. Let's see here. The tricky thing about when the Wacom starts glitching out is I want to write fast, but I can't, or it'll glitch out. So, okay, so I've got delta V equals for the rectangular bit, it was length times width over height times H initial times delta H, right? And then plus 1/2 length times width over height times delta H squared. So we've agreed that the change of changes is two of these. So delta 2 V between evaluated for 3 points, 1, 2, and 3 is actually equal to 2 times the triangular wedge volume. which just gives us 1/2 length times width over height times, or sorry, not even 1/2. It just gives us this, right? Okay. Now we make delta H smaller and smaller. Honestly, I'm just going to conserve space and go to this notation. Make delta H really, really small, right? And at that point, we would start using differential notation and saying d2v equals capital L, capital W over capital H times dH squared. What did we end up finding dV to be? Not d2v. What was dV again?
it was DH times 1/2 length width over height, wasn't it?
Was it the 1/2 one?
It was length
Was it
width over
just
height times I think it was H initial plus H final.
Or sorry, I'm talking about the differential one, not the finite difference. So when we squeezed it all down to 1 point, wasn't it only the linear term that survived?
Yeah.
right?
So it was just length width over height times H times dH.
Oh, okay.
Because we stopped saying H initial and H final because it was really just one, more or less 1 point we were dealing with. So over here, we move those differentials around, which I argue is totally valid. Because if you can move finite difference terms around, why can't you move differential terms around? Equals length times width over height times H. Then we did the change of the change, and we got d2v over dH squared equals length times width over height. And you guys remember what the v function was to start with? V of h.
H initial times with initial
Not
to
not with initials and finals, just for some water level h. So if I said this was h, what would be the volume of that height?
Oh, 1/2 length with height.
Yeah, 1/2 length, and then width was in terms of height, right?
Right.
So we had 1/2 length width over height times h squared, right?
Hmm.
So using finite differences, this was our formula. This was its first difference. This was its second difference, right? And we start to see, you guys already know calculus, so you're like, okay, this is just the power rule. What comes next? What would delta 3 of v be equal to?
0, we're out of H.
Yeah, I mean, like we're definitely going to predict it's going to be 0. How many points would it require to do a change of the change of the change?
5?
So
Wait,
to
because it's
have,
like we have the 2, and then we link the 2 to get 3, and then wouldn't it be 4?
yeah, I think it's just 4, right? We just need an additional point up here. We'll call it H4. Oops. And this one's kind of fun because you can see visually why it zeroes out at some point. Let's see. So I draw this like this. It's like that. Okay, so what we're really doing when we take the third difference is we're saying take the difference of the second differences. Dang, I'm struggling here. Let's see. So the second difference of V evaluated at point from 3 points, 2, 3, 4, minus the second difference evaluated at the 3 points, 1, 2, 3. And we already know what these differences represent, don't we? What do they
Parallelogram.
represent? Yeah, that parallelogram, right? And when I go from this piece to this piece, this is what that parallelogram looks like, right? What does the parallelogram look like when I go from this piece to this piece?
Should look like last parallelogram.
Looks exactly the same. And so we have two parallelograms with exactly the same area, and we're taking the difference between them, right? So that's just going to give us 0.